transpose AY equal to Y transpose AX, min X, max Y, max X, min Y, right? So if I want to show something using Minimax theorem, my task is to construct exactly, right? So to formalize this, what I need to do is construct a matrix A, right? And I kind of know by this idea what should be the rows and what should be the columns. Right? Let me write it out in any case. I think it would be a good idea. Don't sleep, don't look, try to construct the A and see if it works. Okay? And what do I, so I've changed A to M. Let me not do it. A, because I've been talking about A. Let's keep it A. A is the payoff matrix. These are probability distributions in R to the M or R to the N. Correct? So I want to use this, I want to make sense of A, I want to make sense of X transpose AY. Right? Now, looking at this, I should have all the inputs. Correct? Agreed?
So by inputs, mu is applied, right?
No.
By inputs, mu is
No. Mu is going to be a probability distribution over rows.
But then how would we find the intersection? We are taking two inputs at once.
There is no intersection here now. This is a general communication complexity problem.
But again, we have to take in two inputs, right?
Right. So every entry here is some pair X comma Y. Right? And this is some protocol P. Okay? Let's fix some cost C. Okay? So here P, when I say P, it is a protocol with cost C. Now you might ask what C is. Remember, average case is always less than worst case. What we are interested in is saying that there exists a particular average case which is equal to worst case. So let's say C is the maximum over all possible average case protocols. But the probability distribution will have only finite support. Actually, you can't have infinite protocols because your cost is C. So every protocol is given by the transcript. The transcript length is C. Every alphabet in the transcript is at most this much, right? So, and you can even bound the randomness. You can give a fixed amount of randomness. This more than that amount of randomness is, for example, more than R amount of C amount of randomness is not needed. You won't even be able to use it or something, right? So all that kind of things. But no. C is not the worst case scenario. C is not the worst case. Again, in all this discussion, we have a F in mind. F is fixed. If you are lazy, F is set disjointness, right? Let's keep that F in mind, but it is true for any general F. You want to prove that average case, the max over average case is same as worst case.
No, I'm not able to understand why only protocols with cost C are being considered.
Because that will make our task easy. like this will have a well-defined. So what do we want to do? We want to show that, again, we have to define a matrix so that these two things, like I can make sense of these two things. This becomes the average cost, this becomes the worst case. So one way to do it is to say that, oh, let's say this thing is C. This thing is C. Which means for any distribution mu, there is a communication protocol with cost C, which correctly answers with probability more than 2 by 3. And now I want to come up with a randomized protocol of cost C, which works for every input. That's the task I'm doing. Okay. So then I have restricted my P, these protocols, to be only the ones with cost C. Okay. Clear? And now the next question is, what is this entry? Like, cost for the protocol is now C for every input, right? We have fixed that C is the upper limit. Even if they use less, I don't care. Okay, so I guess one important piece is missing here, which I want to emphasize, which is actually needed for all of this thing to work, is what do I mean by a randomized protocol? Right? And you know this, correct? What is a randomized protocol? You have some randomness R, you toss a coin, and then you decide what to do. Do you want to send this bit or that bit? Do you want to compute addition? Do you want to multiply? So on and so forth, right? This is the randomized protocol. But notice that in this case, a randomized protocol is nothing but a probability distribution on deterministic protocols. What I'm saying is, when the decision comes, you don't need to toss a coin when the decision comes. You can toss the coins beforehand, right? So a way to do this would be, you start, you do some computation, you realize, oh, I need to toss a coin. Now this is 0 or 1. Now your computation part differs. Again, you toss a coin. What I'm saying is, finally look at the leaf. There is some probability of doing this computation, but this leaf is basically a deterministic protocol. This leaf is basically a deterministic protocol. So I can think of this randomized protocol as a probability distribution on deterministic protocols. Other way to say it is that when I talk about these protocols, these are all deterministic. And a randomized protocol is a probability distribution over it. Yes, so what is happening is now, what is the strategy of a column player? It is going to be a probability distribution over protocols, which is basically a randomized protocol. So now the strategy of a column player is a randomized protocol, and I can maximize, minimize over that. That's okay. Now, with this knowledge, can you tell me what would you like mx comma y? So this is mij. Oh, why do I like m so much? Right? The input is x comma y. This is one of the rows. X comma y is one of the rows. P is one of the column. What should this be? What should we start with? P is a deterministic protocol. Sorry? Take a guess. Again, important thing, is there probability here? No, P is a deterministic protocol. It is correct or not, right? That's the simplest thing. Let's start with that. Notice things have changed now, right? Previously we said a protocol is correct if it works correctly on all x comma y. But now this is a set of all protocols which have cost c. They might work on some x comma y, they might not work on some x comma y. Right? Clear? Good. Great. So then, if I have an input in mind, I have the matrix A and I have a particular protocol in mind. What is this? Same thing, right? You realize that this is the standard vectors. What is this? AIJ or AJI? AIJ. Correct? So this is but now things are going to become interesting. I is going to be a input distribution, right? Let's call it mu. Okay, and we want to change P to be distribution on protocols. Let's call it P. Right? And now I want to ask, don't guess. If you have an answer in mind, are you convinced that it is correct? Let us start with P being a point protocol. It's a particular deterministic protocol. Then what is this? P is a fixed protocol. Mu is a distribution over inputs. What does this thing give me? You are in the right direction, but I think if you write it down on your pen and paper and think about it, what is probability over? Sorry, P is not a distribution. P I am saying is a particular protocol. Right. Right? Yes, our intuition is correct, but you want to write the complete correct thing because you want to apply maximin. We don't want to give the incorrect proof, right? So this is exactly mu transpose AP if P is a fixed protocol. But how does it matter? Even if P is a probability distribution, this is linear in that probability distribution. Correct? So this and randomness R or P do you agree with this? Do you want to spend some time with it? Okay? If you are not convinced, look at what this thing is. Remember, X transpose AY is summation I comma j, right? So that means Okay, you can take out probability of P first, take the summation, that will give the correctness of probability of P, like of a particular, so right, this is small p, this is big P. Okay, big P is a probability distribution over small p's. Sounds good? Okay. See, you should say okay slowly, because once you say okay, I'm going to ask another question. And if you have understood the previous thing, then you should be able to answer this question now. That's why I said take some time and internalize this. So, this is summation over xy, probability x comma y, summation over p, probability p, whether p is correct on xy. So, this is the probability that my randomized protocol works on x comma y. Now, with linearity, this becomes what is the probability that capital P works on input distribution mu. Sorry. When I say probability over mu and P, my randomized protocol P is correct. What does this mean? This means summation over all my inputs. My input is coming from mu. What is the probability that my randomized protocol works on x comma y? Now this thing is exactly this thing, right? Because what is my randomized protocol? I play P1 with probability P of P1. I play P2 with probability P of P2. So I sum up the probabilities of the correct protocols. I get that, right? Good, right? So this is the mu transpose AP is giving me the probability that P is correct. What is the error probability? Right? So then what do I know about this? Very good. How many bits did you use to describe your answer? Lot. You can describe this answer with like 2 words or 1 fraction. Very long answer. The answer is a number.
So if you want, we can definitely apply the Minimax theorem at same time.
No. We will. That is the next step. We will apply Minimax theorem after this. That is why I said that you want to apply min-max, but you want to set up quantities so that everything has a nice meaning to it. Remember, our A is now talking about only the protocols which have cost at most C. What was C? Under C, for any mu, my error probability was at most right? For every mu, there exists at least one protocol for which this is at least 2 by 3. So if I take the max, this is going to be at least 2 by 3. It will come out to be equal to 2 by 3 because we constructed this C, right? C was the minimum C such that everything worked out, right? So this is exactly 2 by 3. This is the X transpose My, this X transpose Ay is going to be the success probability. I shouldn't say error probability, but success probability. Right? Because I know for every mu, this quantity is at least 2 by 3. For any mu, there exists a protocol which succeeds with probability more than 2 by 3. So that means when I take the max, this quantity has to be at least 2 by 3. Yeah, it depends on how do I define C, right? But yeah, even greater than equal to 2 by 3, things will work out. Okay? So now what do I know? Now I will apply Minimax theorem. So now what do I know? Right? Correct? This is the application of Minimax. Yes.
The set of protocols we are considering are those protocols which have a probability of correctness at least something for all its.
Like in the matrix?
Yes.
No.
So what are those columns then?
The columns are all deterministic protocols which have cost C.
That's it.
A column corresponds to a deterministic protocol which has communication cost C. That's all. The correct protocols are the ones which have probability more than 2 by 3. That depends on whether I am going on average case or worst case or the worst case. In average case, my correctness probability is over inputs also, right? That is why I wanted to write mu transpose AP so that I take the probability over everything, right? Confusion, we can, right? It's a lot to absorb, but these are all small ideas which make sense, right? So once again, remember the intuitive meaning of mu transpose AP, right? If mu is the distribution, P is now a randomized protocol, right? A distribution on deterministic protocols is a randomized protocol. So on this randomized protocol, what is my success probability with respect to this distribution? This is what I am capturing. Correct? Now, by the definition of average case complexity, I know that for any mu, there exists a protocol with cost less than C which works correctly. Which works correctly means exactly means that there exists a randomized protocol such that this quantity is at least 2 by 3. The success probability is 2 by 3. This is the definition of being correct in average case. Yeah.
How do we guarantee that the protocol that exists for mu will be the one that will be the min? How does that?
We started with the randomized protocol with greater than 2 by 3, but when we converted to deterministic,
Oh, did I exchange error probability with the... Let me just... yeah.
I think that there exists some way for everything.
Uh-huh.
Or why would the min get that?
No, you are completely right. I think I have just exchanged the success probability with failure probability or max with the... Yeah, sorry. Yeah, you are right. So what should I do is, yeah, max. Good, you pointed out. Very nice, right? So what happens is, again, I was using weaker. I was saying everything is bigger than 2 by 3, then max is bigger than 2 by 3. That's a weaker thing, right? What I know is that if everything is bigger than 2 by 3, then even minimum is bigger than 2 by 3. Okay? My mistake, look at the correct thing now, right? Min over mu, max over p, mu transpose AP, right? This is the success probability. So fix a distribution mu, I know that there is a randomized protocol whose success probability is 2 by 3. So that means the max over the protocols will also be at least 2 by 3. Now it is okay?
But becomes because we claim that there is a worst case protocol.
No. Remember, how did I define C? So C was max over mu, average case cost for mu. Okay, so what does it mean? For any mu, there exists a protocol with cost C which works correctly on mu. Right? This we will remember. Other way to say it is, you fix a mu, there is a randomized protocol such that the success probability is at least 2 by 3, is more than 2 by 3. Right? There is a protocol which is correct. So since this cost is maximum, fixing a mu, there is always a communication protocol which is correct on mu. Correct? Correct on mu means success probability is more than 2 by 3. Right? With this definition in mind, now if I maximize over p, these are all deterministic protocols, these are all randomized protocols with cost C. And clearly there is a protocol here which works correctly on mu. Correctly on mu means this quantity is more than 2 by 3. Right? So since this quantity is more than 2 by 3, for every mu, even the minimum is more than 2 by 3. Good. I think, so I was using the weaker version here, obviously then I wouldn't get things right? I was saying that, oh, everything here is bigger than 2 by 3, so the maximum is bigger than 2 by 3. That's a very weak statement to make. What I want to say is that everything is bigger than 2 by 3, so even minimum is bigger than 2 by 3. That makes much more sense. Okay, so then I get that this is bigger than 2 by 3. But this also means that max, this is more than 2 by 3. Good, I would have gotten stuck here. If I had taken the opposite definition, I would have gotten stuck here, right? By Minimax. Is that okay? We are good? Right? So I was wrong before when I was writing max-min. With min-max, you get the exact correct interpretation. Right? And you can do min-max, I think you just have to change this with failure probability or something and then things will work out, I think. Not sure, but yeah, I think that's, so, yeah. So this gives me, this expression is bigger than 2 by 3, right? And again, what am I doing? I am maximizing over all randomized protocols, correct? The success probability, right? So this will give me the best success probability within cost C, right? This implies there exists a randomized protocol, call it P0, such that correct? I should say P0. Now what does it mean? This is the success probability of P0 on, in this case, on mu. Right? This is the definition. This is how I understand this quantity. Correct? And now I can take mu to be any probability distribution. In effect, I can take it to be the point distributions. So mu could be probability 1, I choose the input pair x comma y. Then this is saying that my success probability P0 okay. These are same statements. If you fix a protocol, success probability on all x comma y is greater than or equal to 2 by 3 is same as saying success probability on any distribution over inputs is greater than or equal to 2 by 3. Those two are the same. We have done this thing 1,000 times. In linear programming term, the optimal is achieved at the vertices. That's all. Vertices are the point distributions. When you take the all possible convex combinations, you get the convex hull out of it. Okay? This is the same phenomena which is appearing many times. And I know many of you are looking at your watch, but be patient, few more minutes, right? So this tells us there exists a worst case algorithm which works with probability more than 2 by 3, which has cost at most C, right? So this proves Yau's minimax. There exists a randomized algorithm, cost less than C, works on every input. Again, we know what works means. Works means probability is correct with more than 2 by 3. This implies worst case is equal to so over mu case complexity over mu. Again, this is the Minimax theorem, but again when I write this, I have a fixed f in mind. Right? Now, this might seem like a nice mathematical theorem which says, oh, average case, surprisingly, average case complexity is same as worst case. Correct? But the main important thing is using this, you can give a lower bound. How do I give a lower bound? I'm generally interested in, let's say, worst case complexity of set disjointness. And this is actually the way in which the first lower bound for worst case complexity came about. Right? If I want to give a worst case bound, I can show that if I show that there exists a mu such that I have to make sure that I do it correctly. Is less than. Right? For communication cost, right? So suppose I find these are called hard distributions. So I have an input distribution in mind. If I show that for that hard distribution, this is less than 2 by 3, that means the worst case complexity is more than C. Right? Because this is saying that this is not going to be 2 by 3, this is going to be smaller than 2 by 3. If I restrict it to cos C, this is going to be less than 2 by 3. That means this is less than 2 by 3. There is no good randomized algorithm which works for all the inputs. So, what is this saying? This is saying that the average case complexity is not C. Right? If the average case complexity max over mu is not C, then the worst case complexity has to be higher than C. This is saying that there is no protocol of cos C which works for input distribution mu. Correct? This statement is telling you any communication protocol which has cost less than C, its success probability is less than 2 by 3. It doesn't work for distribution mu. That means average case complexity is higher than C. That means worst case complexity is also higher than C. And now even proving this is very, very easy. Once again, because now I don't have to worry about P being a probability distribution. I can reduce it to max over all deterministic protocols. Success probability is less than. If I can find a hard distribution such that all deterministic protocols fail on it, I'm done. All deterministic protocols of cos C fail on it, I'm done. I know that worst case also will be higher than 2 by 3. So, and this, constructing this hard distribution is actually a very nice, very creative endeavor. It is called a hard distribution because you kind of come up with x comma y pairs which are hard to distinguish. So, I will leave you just by one last question. What do you think? What kind of input pairs are hard to distinguish for the set disjointness problem? One element in common, right? So, you take x comma y such that x comma y are completely disjoint or they have just one element in common. These are in some sense, so you look at these kind of things, put a probability distribution over it, and that's what actually Rasburov did and proved the set disjointness problem. This was one of the papers in your list of projects, but nobody picked it. Nobody picked it, right? Yeah. Let's see, if I have time, I will present that. Okay. But these are lot of proofs work like this. I have just given you minimax and randomized communication complexity. There are randomized algorithm. There are many, many randomized settings, all of which benefit from Yau's minimax. Thank you.